So in some ways, this is going to be the first thing that we're going to see that's really kind of new. It's only day 3, so that's fine. I mean, limits, we've talked about limits in a bit more of an interesting way, and like the learning goal that we just took up, the graph, that kind of thing is sort of new, but this is a new kind of question. All the ones we saw yesterday were just MHF kind of questions, getting warmed up, I guess, and this one's new. So what's the strategy? So we're going to look at, I think, 3 sort of different strategies, 3 more strategies today. What's the strategy that we're going to use in this case? And we're going to use substitution, or change a variable, you might call it. Morning, how are you? Yeah. And so the reason why we're going to use this, like part of, it's great to know the strategies, but you also have to know when to use them. And you've seen this in other courses and other areas. Do I solve this quadratic by factoring or by using the quadratic formula? And that's part of the learning, is when to use the different strategies. So I would say this is a strategy. What's an indicator is when I have, something like this. And if I remember back from grade 11, this is the same as this, right? I can rewrite a cube root as an exponential form, as an exponent. So when you have a rational exponent or fraction exponent, whether it's written one way or the other, then we're going to use the substitution strategy. Okay? And so what we're going to do is we're going to let a equal this x plus 8 to the 1/3. And because we're changing the variable, you're gonna see this when we continue the question on the left, but it's not x approaching something anymore, right? Because there's not going to be an x. We're replacing all the x's with a's. So it would look silly if it was like as x approaches something and there's no x in the question. So what we have to do is we have to consider as x approaches whatever it approaches, in this case it's 0, right? So as x approaches 0, what is a going to approach? John? You're on the right track. 2, how'd you get that? Yeah, so you're subbing in, right? We sub 0 in for x. So we sub that whatever value, 0 in this case, because that's what x is approaching. But I get 0 plus 8, which is 8, and 8 to the 1/3 is 2. So as x approaches 0, a approaches 2. So that's really important. And then typically, usually, or really all the time, we're also going to need to rearrange this and solve it for x. So I'm going to do that here. So I'm going to raise both sides to the exponent 3, right? So I get a cubed equals x plus 8, and then subtract 8. So a cubed minus 8 equals x. And that was sort of the pre-work for the strategy, the setup to use the strategy to actually do the substitution. All of that is necessary. I would sort of, I guess, call those 3 steps, right? So there's step 1, step 2, step 3. There's sort of 3 little steps there, and you always have to do those 3 when you're using this strategy. And so now I'm going to get the limit as a approaches 2, and I'm going to replace the cube root of x plus 8. What am I going to replace that with? A. And what am I going to replace x with? The new expression that we've got for x, which is a cubed minus 8. And what do you think we're going to do now? Elif? Yeah, very good. So now you see how this is going to work. Now we have something that's factorable. That's why we did this substitution. So equals the limit as a. So you can go ahead and solve that now. You should be able to do that. Don't copy me. All right, so it's a difference of cubes, and we know how to factor that. It's just formula, really, right? And then when these divide to 1, what do I get left on top? This is a little bit different than the way we usually see it, because usually we're factoring the top, and we have, but very good, that's right, we're going to get just 1 on top over a squared plus 2a plus 4, and then I can sub in, and I get 1 over 2 squared plus 2 times 2 plus 4, which is 4 plus 4 plus 4, which is 1 over 12. Feel okay about that? We're going to do another substitution type. Looks a little different, but we can do one more like that. Any questions? I also want to go back and just touch on something from yesterday, because it was one of the examples we didn't get to. And if you didn't see it, went up on the classroom. So it was this one. And what I have here is a degree 3 polynomial. And we sort of talked about this at MHF when we did applications, where like I know what has to factor out, because the limit as x approaches 2 over x minus 2. So I know that the x minus 2 is what has to factor out. Okay, and this was similar to when we were doing stuff in applications, where we sort of forced it to work out a certain way. So I'm going to do the same thing. I know that x minus 2 has to factor out, so I can use, do you remember factor theorem, remainder theorem from MHF? You should. That's something, and for my class, I remember talking about this, and I said, you know, we talk about remainder theorem for a day, and then we talk about factor theorem, but what we really do for the most part is use factor theorem to factor higher degree polynomials. That's mostly, and so we kind of forget about remainder theorem and factor theorem, that they're a thing. But they're really, really useful. Okay? Because often we want to know if something's a factor, or show that something's a factor, or often we might want to find the remainder of something, right? So it's really can be, they're really useful. So I use factor theorem. You don't have to show this step, by the way, but I was just sort of showing it as showing my thinking. That 2 is a factor, okay? So it factors out, and there's your other check, right? When you do the synthetic division that you're going to have to do anyway, you'll see that it is a factor, so you're going to check it anyway. So you don't have to show that red part, but so we do the synthetic division so that we get the x minus 2 on top, and then I don't have to factor any further. This is one of the things that I wanted to point out. There's no point in factoring further, right? It's not like, and this is where, you know, we teach you all these skills, but then it's applying, when do you apply the skills? And so again, often when we're factoring polynomials or anything, we factor them as much as we can all the way. But that's just because we're practicing that skill. That's because the instruction said factor fully. But in this case, you don't have to, right? So don't bother. That would be a waste of time. I've got what I need after I just factor out, but I do need to find this part because that's what's left, and then we're good. So I just wanted to point that out. If there's any other questions about any of those examples from yesterday, since we kind of ran out of time, make sure you ask. Okay, let's take a look at example 2 here, or B. Yes? Oh, yeah. I'll try. So its limit as x approaches 1 of x to the 1/6 minus 1 over x minus 1. So I'm going to use u this time. Kind of looks like an A. Missing its head. So let u equal, what do you think? What do you think? It's only slightly different from the last question, but Emma, what do you think? Yeah, very good. I could see people thinking x to the 1/6 minus 1. And that very well might work, but we're better off just with the part that has the exponent on it. Don't add more things to it. Okay, so that's the first step. Next step, so we have to do this. As x approaches 1, what will u approach? You just sub in 1 to the 1/6. What is that? Should be an easy one. John, what do you think? It's 1. And then rearrange this, so take the 6th power on both sides, raise both to the 6th power, and I get u to the 6 equals x. So now I have the limit as u approaches 1, u minus 1 over u to the 6 minus 1. And again, I remember saying this last semester, but more and more and more, as the material gets harder, and in high school we only start doing a little bit, and then you get to university and it's like rampant. It's crazy how, we do a few examples in class together, but then there's some examples in the homework that are a little bit different, and that happens more than it did in grade 9 and grade 10 for sure, and grade 11, right? Like, so even something like this is slightly different. Oh, the fact that it's u to the 6. Like, you've seen this before, you've factored these before, but it will make things a little bit trickier, and some people struggle with that. Well, I've never seen an example quite like this, but that's the direction that math is going, right? And I told this story to my class last semester about how when I got to university, and like every test I wrote my entire time there in math, because I took other courses, right? But in math, no questions on the test looked anything like the homework. Like, I can't tell you, it's crazy. You sit down, you're like, I've never seen any of these. It's very frustrating, very, and maybe not every university is like that. Maybe universities have gotten a bit better, I don't know. But it's very disorienting at first, right? It's so different. Okay, anyway, let's go. What do you think we should do to solve this one? What should we start with? You have factored higher degree polynomials like this. Even back in grade 10, you would have done a few of them. But Emma, what were you going to say? Yeah, you could. What else could I do? Can anybody else think of something that I could do? I know I want the u minus 1 to factor out. Could I use synthetic division? Would that work? You'd have a lot of ghost terms. I think that would work. What else could you do? I could do it as a difference of cubes. I could also do it as a difference of squares. And whether you do one or the other, it's going to kind of work out the same way. So let's... Emma, did you start doing it as a difference of cubes? Interesting. Okay, I'm going to do it as a difference of squares, and we'll compare and see what they look like. So as a difference of squares, I'm taking half of the 6, and I get u cubed minus 1, and u cubed plus 1. That's my difference of squares. And now I have to continue, and now I'm going to do a difference of cubes. So the difference of cubes is u minus 1, and there's the thing that I needed, right? And then I have to do the rest, u squared plus u plus 1. And then still times u cubed plus 1. Do I have to factor that part? No, why bother? Is everybody okay with that? And so you see how every one of these questions, they work out a little bit different. And, you know, the more, I guess, versatile you are, or better you are at factoring and seeing the different ways of doing it, the easier time you're going to have if the questions are even slightly different. Emma, how was yours? Was yours this basically the same or different? Or? Yeah, and it was just 2 steps, like very similar, and wasn't harder or easier or anything like that. So it really depends on how you see it. Okay, let's just finish this off and make sure we get the same answer. So this is the limit as u approaches 1. Again, 1 over u squared plus u plus 1 times u cubed plus 1. And now I can sub in, so that's 1 over 1 squared plus 1 plus 1, 1 cubed plus 1. So that's 3 times 2 is 1 over 6. Good? All right. This is actually our last example. I think I said there were 3 strategies. There's only 2 strategies, 3 examples today. And this is the last kind that we're going to look at. What do you remember about solving absolute value equations last semester? How would you summarize that process? Yeah, you split into cases, solve for each case, and then sort of, interpret your answer. So when you have an absolute value, we're going to do very much the similar kind of thing. Okay. So we're going to call this strategy compare the left-hand limit to the right-hand limit. You don't need to know the names of these strategies. These aren't really formal names either. And we're going to use this for absolute value. And for piecewise functions. You know what I mean by that? Piecewise functions are the ones that's like f at x equals has a whole bunch of things, and we looked at some of these yesterday. Usually you're looking at the limit where there's an actual break in the graph. Okay. So let's do the, first of all, I'm going to say when x minus 3 is less than 0 happens when x is less than 3. And so this is going to be my left-hand limit. And so I'm going to say the limit as x approaches 3, and I have to add in, because now I'm splitting into 2 parts, the limit as x approaches 3 from the left. And when x minus 3 is less than 0, what happens for the absolute value? So remember, if the argument of an absolute value is less than 0, then the absolute value function, what it does is multiplies that by -1. It doesn't change the value. So if I put in -2 here, and I had -2 minus 3, that would give me -5. But if I did absolute value, it doesn't change the 5 part, it just changes the negative part. So it's this absolute value is this weird function. It's really simple, right? Remember, it's really simple. It's a simple idea, just get rid of negative. It just makes everything positive. But when we think about the mechanics, like the computationally, what's happening is a little bit different, where it's like, if it's negative, I multiply by -1. If it's not, I leave it alone and don't do anything. So when we're talking about an expression like x minus 3, when that expression is less than 0, I would multiply the entire expression by -1. And so if you remember back from the last unit, whoops, that looks like this. I go negative x minus 3. Right? So I put the whole thing in brackets, the whole expression, whatever it is. If it was more to it, then I would put the whole thing in brackets like that. What's the rest of the question? And then x squared minus 5x plus 6. So I'm going to leave the top alone. I don't think I want to expand that through and factor the bottom. And be very careful again. Don't let this be the mistake that you make with all this high-level math we do, and then we miss the negative when we cross out the brackets, right? So this is -1 over x minus 2. And then I can sub in. So -1 over 3 minus 2, which is -1 over 1, which is -1. Now we get to go back and do the whole thing again. Whoops. So I'm going to let you do this one really, but when x minus 3 is greater than 0, when x is greater than 3, a lot of people get caught up on when we did this in MHF, where does the equal sign go? Which one do I put it on? And in MHF, it should be on one or the other, right? It should be on, depending on the question, but should be on one or the other, and it doesn't really matter which, or it could actually be on both. What about for a limit? Think about that. Should one of those have greater than or equal to 3? Emily, what do you think? Very nice, good application of the understanding of a limit. The whole point of a limit is we don't care about the actual value. I mean, if you put it there, that might be fine. It's not a matter of being wrong, but that's right. For limits, we don't need it. We don't actually care what's happening at 3. We only care about as it's approaching to 3. Okay, go ahead and get started on that one. How'd we do? So, and make sure that we remember that the thing that's different about this one is there is no negative sign, because now this is where that expression is greater than 0. So the whole point is, for the one case it was negative, but for this case it's positive, so it's just x minus 3, and I got 1. And now how do we interpret it? Come on in. Ella? Yeah, so what was the original question? We did all this work, but what was our original question? It was asking us to find the limit as x approaches 3 of that thing. And when we remember the definition of a limit, if it has a left-hand limit and a right-hand limit, fine. But if they're not the same, then we say the limit does not exist. So, and we're going to make a statement on this. Since left-hand limit does not equal right-hand limit, therefore, the limit as x approaches 3 of that function, we have to write it whole thing out, which is a bit of a pain, I know, but we do. X squared minus 5x plus 6 does not exist. What do you think about that? Does it surprise you that limit doesn't exist? That it approaches, like, just thinking it approaches -1 in one case and +1 in the other case. I don't think we've ever seen a function quite like that, absolute value in a rational. So I thought I'd graph it and see what was going on. That's the function. Ugh, weird, eh? So, and there's your absolute value function. And there's your parabola. So you can see that there's an asymptote here where the denominator is 0. But here, it's not an asymptote. And it's like not quite a hole because, again, they're approaching for like, I don't know, it's just strange. But anyway, you don't have to know what it looks like. But thought it was kind of interesting. Any questions about any of that? Oh, I have a worksheet for you. Just do these questions from the worksheet. And then we're going to, and don't throw it in the garbage. I don't know why you would, but we're going to use this again probably later in the unit when we do review. I also have this that I want you to think about. So what I want you to do now, instead of getting started on the homework, is you could think about this on your own first, but then turn to like a friend or a partner or somebody sitting beside you or whatever, and discuss this. Can you think of a real world situation where a function representing the relation would have a point where the limit does not exist? So a real world situation that we would have a function to model. And write an equation of a function that has no points where a limit doesn't exist, 1 point or 2 points. I don't know if there's anything earth-shattering here, but something to think about, something a bit different. Okay, I'll put these back up for now.